Hi, welcome back, Physics 30. So today we're going to talk about the motor effect. So how the motor effect works is you're going to be changing electric energy into kinetic energy so that can turn maybe an axle of a car or something similar to that nature. And then we're also going to be talking about later on, we talk about the generator effect, which kind of reverses this operation. Where can I change kinetic energy back into electrical energy for me? Yeah. So the first idea here is that first of all, I have to talk about what is an electric motor. How does it actually work? Right? And then that's just going to help me just explain how the motor effect actually changes electrical energy into kinetic energy. So here we have a picture of a motor, right? It follows some of the hand rules that we had before. So we got two currents flow, or we got one current flowing through here, but as it travels through the wire, it's traveling in two different directions. So it's coming out one side. Through this side, there's a split right here. It's called a split ring commutator. So I'm going to go through one of the sides here. It's going to travel through the armature. The armature is something that's allowed to spin. You'll see on the little animation that I have later on. It's going to go through one side. It's going to go through the other side. This is perpendicular to the field. So this is parallel, so that has nothing to do with the force. And then it's going to continue on and complete this circuit. The split ring is important here. So what's going to happen is based on my hand rule. So I could say the electron there from north to south. If I did it on this side over, sorry, that side over there, the left side, it's going, the electrons are flowing that way. My field is going from north to south. My force is going upwards. You can see that's already drawn there for us. So this force going upwards over here. Now if I draw it on the other side, the field is still going in the same direction. My electron is now going kind of in that way. My force is down on this side. You can see that. Now, because the force is going opposite directions, one's going up, one's going up, one's going down, it's going to kind of twist the wire around because it can't go straight up. It's attached to the other one by the armature. So when one goes down, the other goes up. It's going to twist. I'm going to think how this is going to work. It's going to twist around. Now, without the split ring there, if the current was always going the same direction through this side of the wire and the same direction on this side of the wire, it would stop. Whenever it gets to the top, the force would always be pulling up, and this one over here, the force would always be pulling down. It would just kind of stop there. So it needs to figure out a way to switch the current direction at a certain point so that this can continue on and actually spin, and when it gets back to this point, you see that the two forces are going up, like that switch, and then continue on as well. So that split ring is really important here. So I have another little animation here from the Mag Lab that shows you this as well. So I can show you this little picture here. So here's my armature. My armature's spinning around here. It's got a battery. They're using conventional current again, so the current's going kind of the wrong way here. That's fine, doesn't really matter. So the current's going up the top, hits this top ring. Current's going to flow through the top ring. You notice that the current on the top ring, top part, is always going the same direction, even though it's spinning around halfway through, and it's hard to see that. Maybe I'll slow this down. Right about there, you can see that the current flips direction all of a sudden. It was going one direction. It's going here, and now it's flipped the other direction. So here you can see this arrow is going towards the right. Right there, now the arrow turns and it's actually going to the left. It does that because it hit this ring, and you can see the red side and the blue side here. The red side's attached to one side of this wire, and the blue side's always attached to the other side of the wire. So when it's up here, the current is flowing through this wire to this red side, through the wire on the top, down and through the wire on the bottom, then through the blue side back to the battery. All right, so the two brushes don't move. This part around here actually moves. So this is a brushed motor. There are such things as brushless motors. They operate slightly differently, but I'm not too concerned about that for this course. So as soon as this ring split on the split ring commutator here, as soon as that brush hits that split, current's no longer flowing through this, but there's enough momentum to keep it going. So it's going to kind of jump past so this brush here is going to jump past from the red to the blue So right now you can see that this is still touching the red. So it's going this way. This one's going towards the blue and then back down. As soon as this jumps to the blue, the direction changes. So now this is going the other direction through this. So now it's going the blue. This guy's now going out the blue and then into the red. Now this one's going into the blue. Now this one's going into the red. So it keeps on switching directions. And what they threw in here, they also threw in these little force diagrams here. So this is the force here. This is the force here. You can use your hand rules to determine the forces. Just watch out. The black arrows are conventional currents, so you'd use your right hand to do that. Now you have to go north-south, and you can kind of see that if I did that. There'd be a force on the top going this way, and if I change my thumb around the other way, or hard to do, kind of hard to do, okay. But it would be going the other direction. All right. Now, you can see that the forces are always kind of going perpendicular here. This one's going out, this one's going out. Now, if it didn't change direction all of a sudden, the current, those arrows would just be pointing outwards in both directions, right, and just be stuck there. So they had to flip to get that wire to go back the same way. You can see it flip there. Now this wire that was on the other side. So watch this one here. It's kind of pointing towards us here. Still pointing towards us. As soon as the current flips direction, now it's pointed away from us. Now it pulls that top wire to the other side and then continues this pattern around and around and around. So that's how the motor effect works. It's using electrical current to produce these magnetic forces that creates this circular kinetic energy. Now, there's other versions of this, like we have here. Oh, not this one. Oh, I actually got rid of it. But there's other versions where, like this one here, where if I drop this down here, I was hoping that this one would work nicely. It doesn't quite work as nicely as it should. Maybe I can refresh it. Let's see. No, this one's been causing problems. I'm just going to shut that one down. Okay, so that's how the motor effect works. That's what the split ring commutator is all about. Is just make sure the current always flips direction so that it doesn't get stuck in one motion. It flips, and then it allows it to rotate and then flip, and then allows it to rotate again. It just keeps on going and going. This is just the exact same thing. Some motors don't need it. If we talk about AC current, there's two types of current. The current that I see in this picture, because it has this little battery down here, where the electrons are always flowing one direction, coming out the shorter side. Remember, you can draw the little arrow to denote that. That's what we call DC current. It's direct current, always going in one direction all the time. AC current stands for alternating current. So rather than just going in one direction all the time, it's going to flip-flop back and forth, back and forth, back and forth. In this case, 1/60th of a second each time. Every 1/60th of a second, it flips direction. And if you have the motor designed properly, as long as it flips direction at the right time, the motor will continue going around in circles. It's just, as long as it's designed properly, it'll work out just fine. Also, one thing, like there's only one armature in this picture. Most motors don't just have one armature. They don't just have one set of wires here. They'll have multiple armatures crisscrossing each other. So there's always a continuous amount of force acting on it. It's not just the two forces. It's going to be a bunch of forces on a bunch of different armatures moving the thing around. And it's going to have lots and lots and lots of different wires and lots of different forces. The more wires you have, the bigger the force, because there's more electrons flowing through the magnetic field. And we discussed that before. Another example of the motor effect is what we call a galvanometer. It measures current that flows through. So this is a two-dimensional static picture, but I also have one here. This is a galvanometer as well. So we've got this ring here. If I just go back to the picture that I had, I got the coil of wire here. I got a coil of wire. I got the two permanent magnets that will have the magnetic field between them. And if current goes through the coil of wire, very much like this one here, when current goes through the coil of wire, current will go in a circular motion. They'll use your hand rule to determine what direction or which side of that coil of wire it becomes the north side of that coil of wire. So if I use my hand rule, Remember, this is conventional current. So if I use my left-hand rule, because that's just going to go opposite direction, my conventional current is going to go the other direction. So it's going to go down the front here, then up the back. So it's going to go down the front, up the back. If I did that, my thumb is pointing towards the left. And you can see that they did that. They had the thumb pointing towards the left, so there's a north side on this side of this magnet right now. All right? So if I turn this on, it's going to flip around. The reason it flips around is because the north side, so let me just flip it back to where it was. Just turn it off. Okay. No. Right. So the north side of the magnet, so now it's going to go in the opposite direction now. So my current is going around the back side. So my north side is still on this side. Okay. But the north side is attracted towards the cell. So the thing turned. So I flip the battery, it switches which side the north is on. So it turns it around. You can see the current is switching direction, so the thing has to turn around to do that. So that when I flip it, the north becomes that side, the thing turns around, so the north is now attracted towards the south. Now, if you attach that to a spring on the bottom, that kind of gives it a little bit of resistance. If it gives it just a little bit of resistance to it, and then attach this rotating cylinder, rotating piece of wire to a needle or something, you can actually measure current. So that's what this is. So when you change this, there's different norths and souths here. It gets attracted to either side. So the north, in this case, it looks like the north is on the bottom, so it's attracted over here. South on the top, attracted over that side, so it gets pushed this direction. So you can measure the deflection, and it's attached to a spring here, a restoring spring. So it doesn't just flip off to one side. If the more current you have, the more force it's going to apply, so the more it's going to bend over to either side. And the less current, the less force, the less it's going to bend. So that's just another example of how to use the motor effect to produce current, use current to produce motion or kinetic energy. In this case, that kinetic energy is stored back into elastic potential energy. Okay. I just want to know if I want to go to the next one here. Yeah, okay. So we're going to stop the video at this point. Just a nice little short video on the motor effect. The next video is going to be on the generator effect, and Faraday and Henry, two people that actually discovered that for us. Okay, I'll see you in the next video. Bye.